Alright, time for another DraftPhysics.com video presentation. Alright, so the physics Michael keeps talking crap, frankly, and it's just the environment's just kind of strange and weird. Like, I didn't think this would be the problem, frankly. Being able to communicate simple ideas to people, and getting rational counter arguments, and then if they're going to do experiments, have them, be really connected to the thing you're talking about. Just didn't see this as, oh, this is going to be the difficult part. But it is, apparently. And the fact that there are so many experiments that just haven't been done is frankly bizarre. The fact that people can't even, the scientists won't even admit that, wow, yeah, all this should have been done already. We already should know the answers to all these questions because it should have been well documented by now. I mean, this is stuff Newton talked about. Now, the problem with Newton is he talked about it in this very difficult language. Trying to make a distinction between what he called motion of something, and he didn't use the word, often enough, velocity and momentum, and they all kind of, because he doesn't use these, he doesn't use the simple, clear words like momentum versus velocity. He talks about motion and movement, and, anyway, there's some reason to be confused. So the other curious thing, the Ian Gosling, his channel's been, removed, presumably by himself, and just be interesting to know why. He has this record of all these proofs, all these vital experiments to the history of science, and has decided to delete them. I don't know. So that would be interesting if somebody has an answer to that question. What's that all about? But anyway, so there's just these simple experiments, and frankly, I will have to do them because apparently nobody else will do them in any kind of careful construction, okay, without, playing games with silly frame rates and all the rest of that crap. So I'll have to figure out how to do it in some better way, but anyway, so yeah, I'll go over so physicist Michael, I've challenged him on a couple of things. He's non-responsive, so somebody else is going to have to get him to respond. But I mean, clearly he did say in his video that he did the hard elastic experiment, and he witnessed the results, and there has to be some explanation for what he's claiming the results were and why he didn't video them, which is kind of critical. But he's also made a claim about this angular rotation momentum argument. And frankly, that's just the completely muddy ground for physics. I mean, they just changed the formula. I mean, they talk about angular momentum, and they have a formula. And yes, they're saying the momentum is conserved. And then they just do the simple thing where they just say, but it's kinetic energy. So yes, the momentum's conserved, which means you got all the energy, you have the same energy in the two systems, one with a 5 mass twice the distance, one with a 10 mass at half the distance. And we're conceding it's conserved. But they're saying that the half mass going twice the velocity has, 4 times twice the energy. And, just because they say so, because it's kinetic energy and that's what they believe. So it's not like the two formulas are in contradiction. It's that the physics is in contradiction still. So it just seems like that's a simple enough experiment. So that's the reason why that's sort of the Ian Gosling subject, is this, whatever it's called, this problem, this inertia problem, that it takes more energy to move lighter things with the same momentum. You can't conserve their momentum because it takes more energy to move them. Okay, and so, that's just too simple, an experiment to do, so I should be able to do it. I mean, I have a bicycle wheel, and I should be able to do the experiment. So we'll just go over that one real quick. So the two experiments I'm doing, all right, the first one is the catapult And I've explained why it's a little better than the lever as an experiment, because you don't, the energy to move the lever. So in physicist Michael's experiment, he was measuring. This is, he did the experiment for the purpose of measuring. So you put something in, you drop it in with a force, you make something leave with a force, and then after it's gone, after this isn't in contact and this isn't in contact, you measure how fast the lever itself is still moving. And somehow that's a significant thing to know, is how much energy is left in the lever. Now, I would argue that your hope is that it's a minimal amount and that it's a somewhat consistent amount. I would argue it has to be consistent. If you put the same momentum in each time, you would have to get the same energy lost in the lever. But the faster you move the lever, the more energy it's going to consume. But who cares? I mean, how could this be relevant? All we want to know is what went in, how much energy went in, and how much energy is coming out. Now, I think everybody in the conversation, this is what they wanted to know. He was the only person that cared about how fast the lever's moving, frankly. So it's like, this is the hanging point, that somehow he insisted that everybody understood that he was doing an experiment about this. He called it angular momentum. Well, even when he said angular momentum, I thought he meant angular momentum of the stuff moving. I didn't think he meant angular momentum of the lever itself. Who cares what's left in the lever? I mean, how could that be terribly important? All right. So to eliminate that problem of what's left in the lever consuming some of the energy, if you use a spring or some other force to create the motion in the lever, then basically if you're going to do theoretically the same action, then it'll use the same amount of energy. So moving this part of the lever twice the distance is the same as moving this part half the distance. So you're sort of guaranteed that it's going to be the same amount of energy, because this can't move twice the speed without this moving half the speed. So the idea is if you have the two mass here and you have the one mass here, you're kind of guaranteed that the lever is going to use the same energy, because for this to go twice the velocity, this has to go half the velocity. This part of the lever has to go half the velocity when I have this out here. So it would be duplicating the same motion it had for the two mass. So you know they're doing the same thing, which means the lever did the same thing, which means the force it consumed is the same amount, which means that you don't have to worry about the lever using, you can have it made out of, doesn't matter how heavy it is, it won't change these results. And that's the important part. So clearly that's the experiment I'm going to try to do better than I already have. I mean, the results from what I already did seem, okay, it sure appears like it's a lot more than 1.4. Their argument is this can only leave with 1.4 the velocity that this left with. So it's only a 0.4 extra. So you don't get anything near twice the velocity. Now I would argue it was really close to twice the velocity and not very close to 1.4. But that's just from my observations. All right, but I'm going to try to do the experiment better. So that's one. Now I have to make more room. I have to, I want to make, Newton did this, I found, using long pendulums, 10 feet. I'm going to have about 8 feet, but whatever. It does make it easier to see what's happening. So anyway, he didn't have video cameras and all that stuff, so he had to do this stuff over and over and figure out, I should figure out what kind of mechanisms he used to see how far something goes back. Maybe a little piece of paper got moved or something. But anyway, so the other experiment's this simple one. So I posed the question directly to physicist Michael. Oh, what the hell? You couldn't see any of that? Gee, that's not too good. It's always something. But I've said that before. It's always something. Always. The hassles of video performance. Anyway, it really shouldn't have been that bad. I don't know how that happened exactly. The turned off. I don't know. Anyway, all right. Sorry about the drawing being invisible. But, you know, shit happens. All right, so that's almost not good enough. All right, so you have two wheels. These are supposed to be identical, obviously, from parallax. They look very uneven to you, so I'll try to compensate for that. Yeah. So the simple argument is that, boy, it still looks bigger. Anyway, that on one of these wheels, we're going to put the 5 mass here, you know, the 1 mass, let's just say, and then we're going to put the 2 mass half the distance. All right, my simple argument is that this is the same energy that this will be. It's the same as the lever. This will move 1 unit of distance. This will move 2 units of distance in the same time and in the same rotation. There's no way to prevent that from happening. And the simple argument is it's going to take the same energy to move this as it is this. So if I put the 2 masses here, you can think about gravity. Now this should work no matter which way I'm spinning them. So try it both horizontally and vertically. But gravity sort of gives you the same amount going up as you get free back when you go around. So eventually, once you get spinning, it shouldn't be a problem. But the point is that there's no inertia, okay, in the sense that it's just the same weight. So if I did put the object here and just throw the lever, you know, the fact is it's the same weight. This would balance. I could have this on one side of the lever, and I could have this 2 mass on the other side of the lever, and we're just back to this point here again, where these two things, the 2 here, the 1 here, will balance on the lever. No problem. And so there's just a logical statement being made. Okay, you're going to say this has more inertia, moving lighter things. I'm sorry, this one. It's harder to somehow move the lighter object. The lighter object resists being moved more than the heavy object does. That's their argument. And physicist Michael proved this one again quote unquote, by having the same spring compression and putting, a 1 mass and a 2 mass. He used a 3 mass, I guess, but for the sake of argument, well, just put the 3. And he got this, okay, we got twice as much momentum. So we have the same spring compression, but we got twice the momentum pushing heavy objects than when we push the light objects, indicating that somehow it is harder to push lighter things. Now I just bring up the simple counter argument that this is exactly the opposite of the intuition of a gun, which seems to find it really easy to get the energy into the bullet, okay? Can't see the gun over there, but there's a gun over there. So, I can't, this is too irritating. All right, see a little gun with a bullet. Easy to push the bullet, and the gun is the thing that's resisting moving. So now the gun has all this inertia problem. It can't collect any energy, and the bullet's collecting the energy really easily. So it's completely opposite this. So that doesn't make any sense. And then he's conceded that in space, these two things, even though this has 2,000 joules of heat, power, thrust, motion, and this only has 2 joules, that if you're in a spaceship, your spaceship keeps going straight. If you throw this out one side and you throw that out the other side, somehow the spaceship doesn't know that this is 1,000 times more energy. Space doesn't realize, so I'm just, you can't see how it's hard to connect all of their dots and say, okay, this all makes sense. I mean, it makes sense to me that, yes, if this weighs the same as this, the weight is indicating how much its inertia is, its pressure, how much it's resisting. It's telling you based on the weight, and that this weight being half as much as this weight, okay, is going to go twice the speed. It's going to go twice as fast as this is. In the same time, this one's going to go twice the distance, and the lever's going to force it, and it's going to makes perfectly good sense. I conserve the momentum. I conserve the angular momentum. So when he says angular momentum is conserved, he's saying kinetic energy is conserved. Well, can you really have it both ways? No. So one of them has to die somewhere. You can't have both. You can't have both answers. Can't work for this simple thing. You can't conserve the mv and then say you conserve the mv squared, because you didn't. You can't conserve both of those quantities. It's impossible. It either goes 1.4 the speed out here, okay, and if you want it to go twice as fast, you have to put more energy in. So this wheel will be harder to turn than this wheel. The same force, the same push force. In my opinion, it's the same momentum. So it takes the same amount of pushing. So you push this one, it's going to rotate 10 times. You push this one, it's going to rotate 10 times. Because it's the same resistance to motion. It's the same total inertia. Okay, it's the total weight. It's moving. The weight will be the same. Alright, so I mean, I've done this so many times. I mean, is you know, the argument is you really do have to choose here somewhere between one theory or the other. This idea that somehow it makes sense for you to say both theories are compatible. Again, in this theory, how is it possible to conserve both these quantities? In the lever, how is it possible to conserve both? Either this leaves with 1.4, or it leaves at twice the velocity and you conserve the momentum. So it leaves at 1.4, you conserve the KE, or it leaves at twice the velocity and you conserve the momentum. But you can't conserve both. It's impossible. I don't know. Yeah. Argument? Alright, well, I still have this drawing here. I figure there's a couple of little details to point out. And in some of these cases, like this catapult will be done horizontally to eliminate gravity. Because technically there is a gravitational difference. I mean, you're only lifting this twice the height that you lift the other object. And to use the same amount of energy, you need to use 4 times the height against gravity. 4 times 4. You need an unequal, because you have half the mass. You need twice the time in the gravity for it to be the same amount of force. But the point would be is that it's probably a minor amount of difference. So this one should have a slight speed advantage, an inertia advantage. The same would be true with the wheel. The wheel is going to be a little bit uneven. You know, you have it laying flat this way. And the idea would be is obviously when you have the 2 mass on it, the wheel physically will weigh more. So there's going to be more weight on the bearing than when there's a 1 mass. There'll be less total weight on the bearing. But there's also going to be the leverage of the extra weight, which is going to bend it just as much, which technically would be the same amount of force on the bearing. I'm just saying it's something to consider. I don't think it's enough of a factor to mess up the experiment, but the truth is that if you do the wheel vertically, the fact is there's just more weight on the wheel when there's the 2 mass. So at the initial condition, the 2 mass weighs more. Just a fact. Yeah. But once it's moving, the argument is then the weights would even out. Because whatever you throw up in gravity, you get back down again. So, you know, it's a tiny amount of initial motion, and then the motion becomes conservative. You don't need any extra energy to keep it spinning, is sort of the argument. All right, a minimal amount. Obviously, friction is going to steal some of the energy, but it's not going to be enough to make up the difference between the number 2 and the number 1.4. 1.4 and 2 should be different enough that you should be able to get the needle to substantially lean towards one or lean towards the other. I'm back. Been a while. I have work to do. Anyway, so this is trial 13 and 14 that Physics Michael did. And I just thought it was worth mentioning. This is the free momentum trial. And so I'll just show you what he claims the data is. Okay, and I can't make any sense out of it. So I don't want to really destroy my calculations. so anyway, I'll draw it in this little space. That's enough. You can see it. So basically, the lever in this case, he puts in energy. This 500 momentums, 554. So we'll just give this a number. Let's not make it confusing. 100. Now we know that we lost 10% when he did the same distance, right? So he does twice the distance with the same mass. Okay, so it's twice the distance from the fulcrum, and he doesn't get back. He gets back a lot. I didn't figure out that percentage. Like 90% comes back this way, 85% whatever, and he gets a reflection here. So what he gets out is, say, 22% without considering the losses. So we know there's a minimum of 10% losses to the lever itself, right? I mean, that was pretty much found out by putting one thing in and shooting another one out, that you're going to have at least 10% losses. This is over the 10%, so it's really 32% more momentum comes out. So he has two, that's the same mass carts, one mass cart, two of them. So he puts one cart in with 100, and he gets two carts out that total one, with the loss of the lever. I mean, again, you gotta almost argue that what's lost from the lever had to come back out too if there were no losses to the lever. But it's 122. Let's just say it's somewhere between 120 and 122 and 125. Free momentum. Now, doesn't that indicate that that's just impossible? That's like, for example, me throwing a rubber ball at a wall and the ball coming back with more momentum. There's like no difference. This is like a rubber ball, and it's like you're saying the ball broke into two pieces, and you got back in the two pieces more momentum than you threw into the wall. So you throw energy into the wall and you get back more energy from the wall. The experiment created this, 22% with the losses, okay? Even after giving the lever, the lever you have to say the lever had some of the energy. It kept some. So these are your, this is your losses to moving the lever. So you have energy in the lever, and you have 22% more momentum. Okay, you have momentum in the lever, and you have 22% more momentum in the objects leaving. And you only put in 100. So you have 10 here, and you have 122 here. So, come on. Nobody will say, I just don't think that can happen. I mean, you won't agree that that doesn't sound like something that's possible? That I could literally make a ball that I could throw against a wall and it would come back, even if it's in two pieces, with more momentum than I threw it with? That there's some way that a device that doesn't have any energy to give, it actually is going to take 10% of the energy, a 10 at least as a minimum. It's going to take that much. Just moving the weight of the lever. The lever is going to keep its momentum. These things have momentum, and this thing had momentum going in. So mindless marbles, this doesn't bother you at all? You're saying there's absolutely nothing wrong with the way he did the experiment. Like everything has to be just right and just perfect, and that this actually did happen. And nobody's ever talked about it. In my whole lifetime, I've never heard anyone talk about the fact that you can throw something at a brick wall, a lever, and you can get back more momentum. I mean, it's all going in the same direction. It goes in one direction in, it's coming out in one direction. It's just coming out in two pieces instead of one piece. But it has more total momentum. Come on, you gotta concede. There's something wrong. Now, I would speculate that there's something wrong with one of his timing devices. that it's exaggerating the red, the timer going in is exaggerating the velocity, so the velocities have all been way too high going in. But I can't, who knows? The fact is when he put them at the same distance, he did get 90% of the energy into the other card. So, all of a sudden now it's 90 and you get 100. How does, it can't happen. You think that can happen? You people actually think that can be the truth, and no one has talked about it. In 200 and 300 years, this has been the truth. And in all that time, the Industrial Revolution, all this time, nobody's realized that you can increase momentum by just banging things back and forth between levers. Come on. There's something wrong with that experiment. It's a reasonable question to ask. How can you possibly not concede that somebody clever enough could figure out how to collect this extra, plus the energy that's still left in the lever? Come on. I did find a comment on this very subject, sort of. Okay, so it's trial 13, it's the free momentum. So the White Henry guy isn't really talking about the free momentum aspect. He's talking about, well, you're saying that because of the reflection you get, you have to double the amount of energy goes the opposite direction because you reverse the direction, therefore double the amount of momentum went into the wall or whatever that nonsense is. And so he's making that kind of argument, but the point is still the same. You have a free momentum experiment, and you have to account for that. And so this is physicist Michael's explanation, which is crap, frankly. This is a great question. Full of response might warrant its own video. Yeah, well, all your free momentum ideas need a video, in my opinion. But let me give a quick, not very quick rundown. The case of the single object bouncing off a very massive object. So again, the steel ball off the anvil. So this is one of my 5-minute videos that he won't respond to. So it's a subject worth a video, but it's not worth responding to the video I've already made making the argument. And this lever launch with the lever fixed to the massive object like the Earth. So again, we're pretending that you people actually believe, okay? And I can show you a Steve Mould experiment. He got the thing to bounce 200 times. Okay, 200 times. The same energy in 200 bounces. And the whole point is that the whole reason you can get all this bouncing is because the things are really hard. That is, the surfaces don't dent at all. And therefore, there is no deformation, so you're not going to lose the energy because you're not moving little atoms anywhere. So it can bounce a lot of times because there's very little losses. And the very idea that you actually think that each time it bounces, it puts twice the energy into the anvil and the Earth is just, frankly, it's just too silly. Anyway, off the very massive object's anvil and the lever launch with the lever fixed to the massive object like the Earth. So again, this whole idea that somehow the Earth can sense the vibration, absorb the energy, and reject it and force the bounce. I mean, things bounce because the other object doesn't move, right? I throw a tennis ball at a sheet, and the tennis ball doesn't bounce back because the sheet moves. I throw it against something that moves. The movement of that object will absorb the energy. It's done. I've used up the energy moving some other object. If I move something, I've used up the energy. I don't know how you could think anything else is true. How do you think that? The more bounce there is just telling you how hard was the object I threw it against. The harder it is, the more bounce I'll get back. The softer it is, that is, the more it deforms or the more it gives and moves, the less I'm getting back. Very massive object, okay, is different than the lever is launching back more mass than was originally incoming. So it's not really launching more mass in the sense that, okay, yes, the one mass is, they're two separate masses, and the two separate masses combined is more mass. So you're getting a reflection in one case and you're getting a push in the other case. But they're both going in the same direction. So you put 100 in, you get 125 plus the motion of the lever out. So you get 130 momentums out. That's an you know. And again, he's basically going to talk about how he could optimize it to get 200 out. You put 100 in and you can get 200 out. All right, anyway. Than originally incoming, both M1 and M2. And because of this, we can arrange scenarios where there can be much more momentum transferred to the large object. So he doesn't mean large object, he just means the two objects that have the same mass will have commensurate. The mass is doubled and the velocity hasn't, and you've just basically doubled your mass and increased your momentum for free. All right. In both cases, the original incoming object has a certain amount of KE, 1/2 times M1 times V squared, in order to transfer more momentum to the larger mass. So there is no large mass. There's the same mass. We want to use the KE, get as much motion being launched into the opposite direction. If the target object is much more massive, then even if there is a large momentum transfer, it barely uses up any of the KE. So the point was, is he was putting the object in and had a lighter mass further out on the lever, which meant it has to go at a much higher velocity. But it still doesn't make any sense. It's the same mass, and at the same distance, it was able to transfer. At a further distance, he got almost the same, a little bit less in velocity, but he got a second object going in the same direction. It's still more momentum. Okay, in the steel ball off the anvil case, I think that's all I need to say. There's only one object, so if it uses essentially all the available KE, so he keeps talking about the KE, you know, the KE is made out of momentum, so you can say the word momentum, it's okay, and use the word KE later. But you have a certain amount of momentum going in, mass and velocity, to go back into the original direction at the original speed. So the reversal of the direction of momentum gives that 200% transfer to the massive object. So again, he keeps, these people, you really do believe this. I mean, you really think that it's possible to have a 100% bounce. 100% bounce. And I put twice as much energy into the thing that didn't move. But if it does move, I'm only going to conserve momentum. I'm not going to get any extra. So if it moves at all, then I'm just going to conserve the momentum, and I'm going to lose a ton of kinetic energy. But if it doesn't move, I put even more energy in. So I lose energy if it moves. I lose kinetic energy, and I conserve momentum. But if it doesn't move, I gain 200% of the momentum. I have momentum 200 going this way, and I have 100 going this way. So I put 100 in, I get 100 back, plus 200 in the thing that's not moving. I can't believe this is physics. I'm sorry, this is so stupid. I just can't believe this is a Holy Ghost theory or something. I mean, it's so convoluted and crazy. How can you believe this is true? I mean, how can you do it? How can you possibly believe this is true? I get 100% back as a reflection, and I got twice as much energy into the object. It's like a photon. If it reflects, it's not going to make something hot. To make something hot, the photon has to be absorbed by the object. If it's not absorbed by the object, it can't make it hot. But you're arguing that I made it twice as hot by having the photon bounce off of it. So something highly reflective gets twice as hot by your theory. If I apply it to photons, it certainly doesn't work for photons. It doesn't work for anything. It's crazy stupid. God damn. All right, in the lever case, we launch more mass backward than was originally incoming. Yes, twice the mass. Okay. Going at 70% of the velocity, which is a no-no. Okay. That being both M1 and M2. If the mass launched backwards is larger, we can get more backward momentum for those pieces using the same total KE. So he keeps saying the same total KE, which just ruins any kind of conversation. The KE is kind of irrelevant because all these objects have the same mass, but whatever. So here he says, this is kind of interesting. I've been playing around with how to optimize this. So experiments we haven't seen. And the best cases are when a 2 mass is much larger than 1 mass and closer, but not too close, to the fulcrum point. The best cases are where the 2 mass is much larger than the 1 mass. So you have a very heavy mass and you're putting the energy in with a fast mass, I think is he's saying, but not too close to the fulcrum point, such that after impact both M1 and M2 bounce backwards with the same speed. The needed R distance can be calculated. I don't know. The amount of change in momentum you can get for this mass attached to the fulcrum maxes out at 1 plus square root of M plus M2 divided by mass 1. The number's 2, I think. Okay, so that's the best you can do is 2. But whatever. In terms of mechanics, when the 1 mass hits the further distance, even though the force of impact might be small, it generates much larger forces at the 2 mass location closer to the fulcrum, and even large forces at the fulcrum itself. So this really doesn't happen. So they do this with ballistic pendulum, to measure the force of a bullet. And the momentum the bullet has doesn't come out to be more than the recoiling gun. It's the same momentum. So the momentum number's really low. Okay, but let's see, momentum. But there's a balancing act. You're really saying that the gun has 2 joules of kinetic energy. The gun's recoil is 2 joules of kinetic energy. The bullet has 2,000. But when you go to measure it, you don't get 2,000 back. You can't get 2,000 joules to move the gun with. All you can get is the momentum out. The 2. All right. But there's a balancing act. If 2m is too far from the fulcrum, there's too much leverage during the hit, and m1 will just reflect backwards with most of the original velocity. So isn't that funny? Yeah. So if it doesn't move, you only get back what you put in. Proving the point, essentially, right? And so all he's saying is that when you can get it to move just a tiny bit, that tiny bit will be 200 times the original momentum you put in. So as soon as it moves a little bit, you'll be guaranteed 200 times the momentum you put in. And we'll be back to the anvil case. If 2m is too close to the fulcrum, there's not enough leverage, and m1 will just knock through the lever, barely even being affected by the lever. I don't know what that even means. Yes, you put a feather on the lever, it's not going to work. Like I said, there's enough in here that I might make a separate video on it. The whole idea of free momentum sort of deserves a video, because you're basically saying you can create free momentum. That sounds like free energy. I think it sounds like free energy to anybody with a brain that works. So you sort of have to account for why you can't collect the extra momentum. Especially when it's both going in the same direction. It seems like that would be pretty easy to collect. and some of the methods for calculating the optimal conditions. I'll try to make time for this in the next few weeks. Hopefully this gives some of the key points. So White Henry was completely satisfied with that babble, which is really surprising. So if the object's mass is only 4x the starting mass, you'll get more than 300% decrease in linear momentum, for example. I don't know what he's saying there. But anyway, it's just... Sorry, this is a silly theory. Things that don't move can't have momentum. Things that aren't moving can't have momentum. I'm sorry, they can't do it. And this whole idea that the Earth could give a shit is amazing to me. That you really think the Earth cares there's a ball bouncing on an anvil, and somehow the Earth is feeling that ball as if it was twice the energy, because somehow the Earth has to throw the ball back with twice the force. It has to use twice the force to reverse the direction of the ball, when the obvious answer is no, it doesn't have to use any force at all. So I guess the real test of this would be, okay, so if you had a mirror in space and you reflected light off of the mirror, would the mirror move? See, that's already been done, right? So that little photometer thing, right, the little spinning thing inside of the vacuum. When you have a complete vacuum, you can't make this extra momentum thing happen. The side that absorbs the light moves with the same intensity as the side that reflects the light. There's no difference. And you have to have something less than a complete vacuum, and then it will spin, but it's spinning because it's playing with the atoms, it's heating the atoms in the vessel, and that's what's causing the extra pressure on the white side. So reflections don't create more push, okay, than absorptions. And I guess, the key point would be is that absorbing doesn't make something move either. I mean, you would think that absorbing would be a more obvious taking of the momentum. Yeah. So you could see that it would be a 100%, but 200%? No. I guess it's just worth saying that photons aren't the same as tennis balls. So I guess I would argue that yes, photons are working with moving electrons, and electrons are dragged, and so in space, and so they're going to have to be obedient. But big giant material objects aren't being affected by drag, and so there is no obligation for them to absorb to create a reflection. They can just reflect and not absorb anything. Yeah, I mean, really, the real test is you put a mirror in space and you point it towards the sun and you see if the mirror gets pushed. And I would argue the simple answer would be no, it won't be pushed. All right. So that was interesting. So we already had a response that, again, it's just, it doesn't really account for the problem. And free momentum is, frankly, you got to have a good answer for how free momentum isn't something you can capitalize on. That anytime you increase the momentum through a black box experiment, you have a black box, you put 100 in and you get 130 out. That's sort of a chain reaction thing. That's the kind of thing where you should be able to take advantage of it and keep making that 33% over and over and over again for free. All right. So it says nail in the coffin. Yeah, that was you're done, DraftScience, you're done. Yeah, I don't think so. I wonder if there's a Physics Michael response to that thing. Oh, so this is the guy who was the doxer, and he asked him very nicely to quit being an asshole instead of just blocking him. Um, so you got a few of these little numbers wrong. Yeah, we already did that crap. So the one we want is, yeah, you didn't respond to my correct prediction. Yeah. Anyway, so he called him a sock account. Where the hell is is this it? No. There's one that has a whole bunch of replies. Where the hell is it? Is this the wrong? Oh, this might be the wrong video. Yeah, this is the launcher video. Okay, I want the other video. Alright, well, maybe we'll save that for next time. I'll read some other comments where, physicist Michael just keeps talking about angular momentum, and as I pointed out, he's talking about measuring the momentum of the lever after the objects have left, which I don't really understand how that can tell you anything. How much energy is left in the lever isn't going to tell you much, except how much energy you didn't get into either one of the carts. It can't tell you anything else. But anyway. Alright, I'll call that a video. So, till the next time, and such.